Antiderivatives. Okay, so if you are a physicist, you want to know the velocity, so you know the velocity of your particle, and you might want to know the position of the particle at some time. So you know that the derivative of position equals velocity, right? That's the relationship. Okay. If you're an engineer that you know the rate at which water is leaking from the tank, you might want to know how much water leaked from the tank. So like the rate at which water leaked from the tank, that's going to be like a dy dx kind of a thing. And you want to go back to y somehow.
So this is when we turn to the engineer and say, we don't always get what we want.
Not that hard. You might also know how fast your population is increasing, which also is like a rate of change or a derivative, right? And you want to go back to how big is the population at a specific time. And so all of these problems involve taking a rate of change f and finding a function that we're going to call capital F. And that function, and for that function f, the derivative of capital F, so capital F's derivative must equal little f. So it's a puzzle. It's like I took a derivative of something and got this. What was my something? And this thing is called an antiderivative. It's a bit like factoring, right? You multiply two things together and you get this stuff. What were those two things you multiplied together? It's a little bit like that process. Oh, where?
Called a antiderivative.
Oh, so an, I don't like that either. An antiderivative.
Does this get from the derivative back to the original function?
Yes, and it's not easy. So it's going back from the derivative to the original function. So you're taking the derivative back to the original. And the way that, at least for now, you're going to tell me that you've done that, if the function's called lowercase g, your antiderivative is capital G. There's a symbol that says take antiderivative. We're not going to use it yet. This book doesn't use it yet.
That could be difficult considering constants go to zero.
Ah, look at that. We'll get to that. So a function capital F, and notice if I called it an antiderivative when I did my grammar right, except for the antiderivative. The is specific, as in the one. And means maybe one of many, and for the reason you said. Because of the constants, if the derivative of your function equals the original function you had. So think about this. What would an antiderivative of f of x equals x squared be?
1/3 x cubed.
Capital F of x equals 1/3 x cubed. Do you guys buy that? If I take capital F prime, I have 1/3 times 3x squared, which is just x squared, right?
Wait, what if there's
Yeah, we'll get there, okay? So do you guys, at least before you start, okay, I know you're a second ahead of everybody else, okay? So just stop, wait for a second. So when I think about x squared, I'm like, okay, x cubed's derivative is awfully close to x squared. It has an x squared in it, right? So if I guessed x cubed, its derivative is 3x squared, right? I just need the 3 to not be there. So if I add in a 1/3, that takes care of it. Does that make sense? That's how I kind of reason through it. I kind of guess and check. I'm like, okay, well, this guy's derivative is that, so if I just add this constant in, it'll make it work. Can you think of a different function whose derivative is also x squared? 1/3 x cubed plus, pick your favorite number.
70.
Is that derivative still x squared? Make another one. F of x equals, I'll make one, 1/3 x cubed plus sine of 7. The sine of 7 is a constant, and its derivative is 0, right? You could each make up your own one, couldn't you? And they could all be different. Does that make sense? So the way you say this generally is you say capital F of x is equal to 1/3 x cubed plus capital C. And I'm pretty sure that WebAssign makes you use a capital letter when you put in your answers. Okay, so just FYI, be aware of that. I'm pretty sure it doesn't let you use lowercase c. In the direction that says use plus capital C for your constant, it means it. So.
If I'm mistaken, I believe lowercase c is the speed of light in vacuum.
I wouldn't know, but that's possible. But for some reason, capital C it is.
So that should be 3 times 10 to the 8th.
What?
3 times 10 to the 8th meters.
Okay. So if capital F is an antiderivative, so kind of like how the first thing we had was 1/3 x cubed, the most general antiderivative is that antiderivative with a constant, an arbitrary constant added on. So C could be any constant. You'll need more information to figure out what that C is. You can't find it unless you're told something about the function's original behavior, but that's the general antiderivative. Okay, so sine. So capital F. So my first guess is cosine. Does that make sense? And then check by taking the derivative. What's the derivative of cosine? Negative sine. So put a negative in front of it and it fixes it. And then plus C.
So would it be like a word problem? Like, C is.
We'll get to those. But yeah, there'll be instances in which you can figure out what C is. Okay, this one. So whose derivative is x to the 6th? Well, if I had x to the 7th, its derivative is 7x to the 6th, right? But I don't want 7x to the 6th, I just want x to the 6th. So how do I get rid of that 7? Times by 1/7. And then once again, you add your constant plus c on the end. Okay, so using that pattern, what's the antiderivative of x to the n gonna be?
1 over n plus 1.
X to the n plus 1 is correct, but this should be 1 over n plus 1 as well. Yep, and then plus c. Now there's one slight issue there. N can't be one thing.
0?
Nope,
Negative 1.
-1. So you were kind of right, Jimmy. N can't be -1 because that makes the denominator 0. And I'm just going to add this in because you definitely have space to write it. If n does equal -1, then f of x is x to the -1 or 1 over x, right? Does that make sense? Yes.
For the 1 over n plus 1, is that f supposed to be just?
Oh, that should be regular f, not f prime. Yes, thank you. Yep, this should say f, sorry. Okay. So what is,
So why does it just take it out? Because if n doesn't equal 1, why does it?
say that again? I just couldn't hear it.
So if n did equal -1, why does it cancel?
Why is that a problem? Because if n does equal -1, what happens to this fraction? What do you get?
1 over 0.
Uh-huh.
So how does it cancel?
It doesn't matter. 1 over 0 is bad. When you have 1 over 0, it's just like, I don't care what to do, breaks down. Okay, so just, you can't have 1 over, yeah, if 1 over 0 just doesn't work. So, and you have to handle that case separately. So, but when you do plug in -1 for that exponent, do you agree that you get 1 over x? So what is an antiderivative of 1 over x? Whose derivative is 1 over x?
Natural log of x.
And the technical thing with this is a little bit tricky, is you have to say ln absolute value of x. Remember that guy's derivative also was 1 over x, and because this 1 over x includes both positive x's and negative x's, this does too. Okay, so let's anti-differentiate x to the root x, which is x to the power of 1/2. We can use this formula, or the same pattern that got us this thing, right? So capital F of x will be x to the 1/2 plus 1, because when you take the derivative, you take away 1, but to the antiderivative, you add 1, right? Do the opposite. And then divide by 1/2 plus 1. So what is 1/2 plus 1?
3 2s.
And then if you divide by 3 2s, it's the same thing as multiplying by
2 thirds.
2/3.
That's a quicker way of doing it than I did it.
There you go.
I was plugging, so
But the point is that, and then if you take the derivative of this thing, capital F's derivative will be 2/3 times 3/2. Notice how those cancel out nice and pretty, right? The new power in the x is going to be 3 2's minus 1, and which will be 1/2, right? So it'll be 1x to the 1/2.
How many levels of antiderivatives are there?
Oh, you can keep doing it. As in you could, like, just like you can differentiate once, you can antidifferentiate more than once. Is that what you were asking?
Seems like it would get ugly.
It can, but not necessarily.
Will we be asked to do that?
Yes, actually, we're gonna do a few of those. You just knew we were gonna go there. With this one, I'm almost always gonna take this shortcut. This number is always the reciprocal of the exponent. Does that make sense? Even in this case, right, the reciprocal of 7 is 1/7. So my method, which is not perfect, but it's just what I choose to do, is I always figure out the exponent first, and then I put the coefficient in front after that. Okay. All right, so big bunch of formulas. But if you know your differentiation formulas, this is really not that big of a deal. So if your function is x to the n, what's the antiderivative of that? X to the, and I'm just gonna say over n plus 1, right? Plus some constant c. The only kicker there is n cannot equal -1. So whose derivative is cosine? Is it sine? Yeah, so it is sine. Okay, plus c. Whose derivative is sine? Negative cosine. Because cosine's derivative is negative sine, so you've got to add a negative in there to compensate. How about whose derivative is secant squared? Tan. Whose derivative is cosecant squared? Cotangent, and that's almost right because remember all the co-functions have negative derivatives. So you have to add in a negative there as well. Okay, whose derivative is secant x tan x? And then whose derivative is cosecant cotangent? Negative cosecant. Okay, whose derivative is 1 over the root of 1 minus x squared?
Inverse sine.
Inverse sine. It could also be negative inverse cosine.
So either one.
Either one, but is most commonly sine inverse.
So it could be either one.
It could be either one, sine inverse is simpler. But I mean, it's not, it wouldn't be wrong to say negative cosine inverse of x. That actually is, it is true. If you want to do that, I'll know, like I can figure it out. I think WebAssign probably will too, but I'm not positive. How about 1 over 1 plus x squared? Inverse tangent.
What would be the alternative? What else would we write other than inverse sine?
Negative inverse cosine. Because the derivative of sine inverse is 1 over the root 1 minus x squared. The derivative of cosine inverse is negative 1 over the root 1 minus x squared. So as long as you compensate with the negative sign, it officially is also true that negative cosine inverse is also an antiderivative. Okay, 1 over x, the bit tricky thing is you do have to have absolute values around that x when you antidifferentiate. What's the antiderivative of e to the x? E to the x. Okay, a to the x is a little bit tricky. The derivative of a to the x is what? Ln a to the x. So if you antidifferentiate, you have to have a to the x over natural log a. Because then when you take the derivative of your answer, the natural logs of a's will cancel. So if I took the derivative of a to the x over ln of a, that over ln of a is just a constant, right? It'd be 1 over natural log a times natural log A times a to the x. And then they go kaboom. You just get back a to the x. That's probably the trickiest one that you're gonna see today. And these last two things aren't really formulas, because they're just kind of rules, is that if you've got a constant times a function, you can do constant times antiderivative. Much like when you had a constant times a function, you could just leave the constant alone, take the derivative. And for adding two functions, you can do antiderivative of first plus antiderivative of second. There's no rules for products and quotients. Don't make any up, they're gonna be wrong.
Are you need to add a constant to those last two?
Yes, I should add, yes, I should add constants to both of them. But there are no product or quotient rules, and there actually really don't even exist any, period. Like there aren't any quotient rules, period. But the ones that you're gonna make up are definitely gonna be wrong. Okay. So let's use this. Find the most general antiderivative of the function. So capital F, mostly this is just what I'm gonna call the reverse power rule. So what's the antiderivative of x to the 20th? 1 over 21, x to the, The 4 doesn't matter, right? Just kind of leave it alone. X to the, and then it'd be 4 over 11, because you could do 4 times 1/11 makes 4/11ths. What's the antiderivative of 8? 8x, great. And then don't forget your plus c's. Okay. Capital F of t. All right, the antiderivative of cosine is sine, so 3 sine t minus 4. What's the antiderivative of sine? Negative cosine. And then plus c. And the negative times the negative can multiply, right? Plus 4 cosine t. And it should be really pretty simple on a lot of these questions. Actually, check your answers. You can just differentiate, okay, 3 sine t, the derivative is 3 cosine t. Cosine's derivative is negative sine, so I get negative 4 sine t. You can check your answer by taking the derivative, right? It's kind of like the factor multiply thing, right? You can check factoring by multiplying.
If you're multiplying correctly.
And if you're differentiating correctly as well, right? I mean, that also, both parts of the checking process matter. Okay. Find all functions g so that g prime equals stuff. Now, the problem with this is right now, this is a product. You do not have a product rule, there will not be a product rule, don't make one up, you're gonna be wrong. So you have to make this so that you don't have to use any, there's no product anymore if you can. Just distribute, yeah. So g prime is 4 sine x plus 2x to the 6th plus, when that x multiplies that by that root x, what do you do to the exponents? 3 over 2, you add them. In this case, notice also that the original problem, it stated this is g prime. Does that make sense? They told you that. So if you anti-differentiate, what function are you going back to? You're just going back to g. Not even needing capital G because it was given as g prime.
G of x.
If it was g of x, then it'd be capital G. Yep. Okay, so what's the antiderivative of 4 sine x? Negative 4 cosine x. How about the antiderivative of 2x to the 6th?
2 over 7 x to the 7.
And then x to the 3 halves, well, what's 3 halves plus 1? 5 halves, so the coefficient there is 2/5. So negative 4 cosine x plus 2/7 x to the 7th plus 2/5 x to the 5 halves plus c. On these, you never ever have to find common denominators because the plus c messes everything up. So no need to do anything else, any kind of simplifying here. Okay.
That's not so bad.
No, it's not so bad. I mean, it's just, and a lot of the tricks that you learned, we had to use those same tricks for derivatives. It was faster to do so, right? Okay, this one involves a similar trick, except for we have division. There is no quotient rule. Don't make one up. It's going to be wrong. Okay.
Just push it up there and
So push it up there. So I'd say if you say 4 secant x tan x plus 3x to the 7th minus root x. A lot of you want to say times x to the negative 2, which is totally fine. That's not wrong. When you distribute that x to the negative 2, what happens to your exponents? They add. They're just like before they add. Even though it's a negative number, 7 plus negative 2 is 5, right?
it says
So 4 secant x tan x plus 3x to the 5th, right? So if I say exp add, right, that's, oh, that should be minus as well, shouldn't it? Minus. So what's x to the 1/2 times x to the negative 2? When you add 1/2 to negative 2, negative 3/2. What is another way to do that? If you divide, what happens to the exponents? They subtract. You could do 7 minus 2 gives you 5. 1/2 minus 2 gives you negative 3/2. Subtracting 2 is the same as adding negative 2, isn't it? Okay. And now this was f, so we're going to say capital F. Okay, what's the antiderivative of 4 secant x tan x? Secant, 4 secant. Okay, how about 3x to the 5th?
3/5,
X to the 6th. X minus, all right, x to the negative 3/2 plus 1. So the coefficient will be negative 2. Yep. 1/√x is correct. I just didn't get there yet. So this will be 4 secant x plus 1/2 x to the 6th plus 2x to the negative 1/2. Dane, did you get the 2? Okay. So that's 4 secant x plus 1/2 x to the 6th plus 2/√x plus c. Does that make sense? Sometimes these things involve tricks. And the only way to see all the tricks is to do a whole lot of problems. I mean, there's just no way around it.
Do you have to bring it back underneath to a square root?
No, if I don't specify, you have to. If I might specify that I want all negative exponents rewritten as positive exponents, but if I don't specify, I don't think so. All right, this one, there's no product rule, so you might as well just distribute. And that gives you secant squared x plus,
So I guess that's a common mistake. People just,
it is a really common mistake, so yeah, I'm trying to like say it a gazillion times so you don't make it. We'll see if it helps. Like a broken record. No product rule, no product rule, no product rule, no quotient rule, no quotient rule. Okay. But now it should be really obvious that what is the antiderivative of secant squared? Tangent x. What is, there kind of is a reverse chain rule. Yep, there is one of those. What is the antiderivative of secant tan? Secant plus c. But it's not as cut and dry as the regular chain rule. Yep, section 5.5 is the last section of new stuff in this book. You have to know that one well for calculus 2, okay? I'm telling you now. All right, tangent squared. You do not know a function whose derivative is tangent squared, do you? No. But you do know that, well, you know that sine squared x plus cosine squared x equals 1, right? So how do you get the identity that involves tangent? Divide by? And that will make tangent squared x plus 1 equals secant squared. So in my head, I think, okay, tangent squared bad, secant squared good, right? I can change my tangent squared into secant squared if I know this thing, right? So what is tan squared equal to? Secant squared x minus 1. And then can you antidifferentiate that? Yes, right? What's the antiderivative of secant squared?
Oh, you haven't started taking antiderivative.
No, it's still, no, it's still, I was just rearranging so I turned it into something where I could take the antiderivative.
It'd be helpful if you did that ahead of time on the test.
I won't always do it ahead of time, because part of it is, can you recognize, okay, tangent squared can be changed into secant squared, and I know the derivative of that thing. Does that idea make sense? That's the thing I'm checking that you can understand. Okay. How about number 7a? What's the antiderivative of e to the x? E to the x, how about 2? And don't forget that's it, 2x, that's it. E to the x plus 2x plus c.
So anytime we see a constant, we just know it's constant plus x.
Mm-hmm. Yep, exactly. What if this one? So capital H, antiderivative of 5 to the x. 5 to the x over ln 5. And is minus 2 sine x correct? I always just do it and then check by taking a derivative. Yeah, sine's derivative is cosine, we're good. And then plus c.
Don't think that would be a good method, just think of a random function, test it to see if it
Well,
works.
no, it's not completely random. I know sine and cosine go between each other, like they flip-flop back and forth. I just don't, keeping track of the sign is just tricky. That's all I'm saying. It's an educated guess, not like a random guess. I don't guess e to the x.
Yeah.
Okay. No quotient rule. There is no quotient rule. Still no quotient rule, guys. So how about we divide everybody by x? So we get, what's 2x squared over x? 2x. X over x makes? And then 5 over x, right? And that's still regular f. Now capital F, antiderivative of 2x is actually just, well, 2x squared over 2, which is just x squared, right? What's the antiderivative of 1? How about 5 over x? That's really 5 times 1 over x, right?
So 5 natural log of x.
Officially, you need absolute value bars, but yes. So x squared plus x minus 5 ln absolute value of x plus c.
If we forget the absolute value bars on a test.
You will be wrong. Yep, you will lose a point. Yep, you definitely have to have them. And it's because, it really is because this function is defined for both positive and negative numbers, and you want the antiderivative that's defined for that stuff as well. And we did talk a little bit about the fact that ln absolute value x's derivative was just 1 over x, right? We did discuss that really briefly. We broke it into 2 cases, one where it was regular x, one where it was negative x, and the derivative was the same in both cases. Okay, this one, okay, don't kill any kittens, but there's still no quotient rule. Okay, so what you can't do, don't say 2x squared plus 5 over x squared plus 2x squared plus 5 over 1. That's definitely bad. People do that. Don't cancel those x squared. That's also wrong, okay? So all sorts of bad stuff. In the last question, we technically did division. It was just you could divide each piece individually, right? This one, you're going to use long division. And we have to be dyslexic and put the numbers in the right spots. So I always revert to stuff I can do. I do 7 divided by 2. That's the same thing as 2 going into 7 like this, right? What does yours say?
It's x squared plus 3 over x squared plus 1.
Because this one is in your homework and I changed it. Okay, x squared plus 3 over x, but the same thing holds true, it's still long division. Okay, so using this as your sort of guide, who goes underneath the check mark? X squared plus 3, and who goes outside of it? Yep. Does that help? Oh, this helps me immensely, but I don't know about you guys.
Could you have just raised it up there and
Nope.
made a big messy thing?
Nope, because you can't distribute when the power is -1. Okay, so what do you multiply x squared by to make it match x squared?
1.
1. And you take that away and you're left with a remainder of 2. So that means your function f of x is equal to 1 plus 2 over x squared plus 1. That's not my answer, but that is my original function. Does that make sense? That's the starting point. We haven't taken an antiderivative yet. This is just the original function. How could you check that that's the same thing as regular f? What would you find? You find a common denominator. You multiply the 1 by x squared plus 1 over x squared plus 1, which will give you x squared plus 1 plus 2, or x squared plus 3. Okay. But now you can antidifferentiate. So what's the antiderivative of 1? Mm-hmm. And what's the antiderivative of 2 over x squared plus 1? Nope, because it's x squared, not x. Think about that as 2 times 1 over x squared plus 1. Whose derivative is 1 over x squared plus 1? Tan, almost, tan, no. Tan, somebody said it, inverse, 2 tan inverse x. I love that random like guessing like everything. 1 squared, 2. It's great. No, if you ln of x squared plus 1, if that was your function, its derivative is 1 over x squared plus 1 times 2x. And so that additional x that comes from the chain rule isn't actually present here, which is why it's not that. This is the kind of stuff we're going to deal with in section 5.5 when we talk about the kind of the reverse chain rule thing. It's called substitution.
So we always need to look at that x squared plus 1 or root?
Yeah, or an x squared plus 1, and there can't be an x in the numerator or it is something different. And this section is supposed to be really easy ones to spot. So it shouldn't, generally speaking, be ln of anything but x, or a tangent of anything but x, or a different variable y or u or something if that's the case. But there should almost never be anything inside your inverse tan or inverse whatevers or ln's or sines or cosines. To deal with like cosine of 2x, we have to know a little bit more. Okay. All right. Find f of x if f prime of x is x times root x and f of 1 is 2. Okay, so to find f, you're going to have to antidifferentiate f prime. And to antidifferentiate f prime, there is no product rule, never, still no product rule. X to the 1 power. Did you say 3/2? I just couldn't hear it. Okay. And there's this additional information that f of 1 is equal to 2. That's going to let you find c. So just first find f with the c in there. So what's the antiderivative of x to the 3/2? 3/2 plus 1 will be 5/2. Coefficient will be 2/5, and then plus c. Okay, that's your first step. It doesn't need to be capital F in this case, because I was given it as f prime. Does that make sense? Okay, so now you know that when you input 1, you get 2. Does that make sense? That's what this f of 1 equals 2 means. So that means that 2 will equal 2/5 times 1 to the 5/2 plus c. Like the y you get out is 2 when the x is 1. right? So that's 2 equals 2/5 plus c. Can you find c from that? You'd take away 2/5? Were you saying multiply by 5, Natalie? No? Okay, but it would work if you did that, though. So that's 10/5 minus 2/5. My c is going to be 8/5. Do you agree? So your function f of x is 2/5 x to the 5/2 plus 8/5. This thing is often called an initial condition. You're given some information about the function. Is that all right? Okay, unless you were told that you couldn't figure out what c is. All right, this next one, we are told what the second derivative is. I want you to go back to the original function. So I was asked, like, could you do this process more than once? The answer is yes. So if I have the second derivative, how many times have to do the process to get back to the original? Twice. Once back to the derivative, and then once more to back to the original. And I'm told two things about the original function's behavior, that when I plug in 0, I get 4, and when I plug in 1, I get 1. Okay, so since we're given this thing as f prime prime, on our first antidifferentiation step, it is now f single prime. So 12x to the, what becomes the new power? Third, and then over 3. 6x to the over 2, and 4x, and then plus c. And let's just reduce those coefficients. 4x cubed plus 3x squared minus 4x plus c. You can do that in one step. Like, you can divide 12 and 3 in one go if you're on top of it.
I like that. Will you bring the power down each time? It's pretty smart.
Yes, it would.
So what do you do, so the c becomes a cx?
The c becomes a cx in the next step backwards, yes.
Another c?
And we're going to add, like, well, pick a different letter because otherwise they mean the same thing, so add d. So this will be 4x to the 4th over 4. Somebody thought this problem through, right? 3x to the 3rd over 3. 4x to the 2nd over 2. And the antiderivative of c is going to be cx. You're going to have to add another constant. I'm going to call it d. Sometimes people call them c sub 1 and c sub 2. But, different letters is acceptable as well. Okay, so just simplify a little bit. We've got f of x equals x to the 4th plus x to the 3rd minus 2x squared plus cx plus d. And your job is now to use the information that you're given to find the values of those constants. D is 4. Do you guys agree with her there?
Yeah.
That's really easy to see, right? You plug in 0, that zeroes out everybody except for d, right? So since f of 0 equals 4, d equals 4. So your function f of x is x to the 4th plus x cubed minus 2x squared plus cx plus 4.
Now you plug in 1.
You plug in 1, yep. When you plug in 1, you get out 1, right? So 1 goes in for x and 1 goes in for y as well, right? So 1 equals 1 plus 1 minus 2 plus c plus 4. Well, it's f of 1, but f of 1 is equal to 1.
The c is negative.
Do you guys agree that c is negative 3? And so your function then is f of x equals x to the 4th plus x cubed minus 2x squared minus 3x plus 4.
Not so bad.
It's not so bad.
It means bad's coming.
No, there are a couple of questions that are challenging that we're going to get to at the end, but they're just, I think they're kind of cool. This next one's not bad. Is 90% not bad and 10% a little bit hard? Okay. So this is a similar question, it's just phrased a bit differently. You have the acceleration of a particle, you know the initial velocity of the particle, you know the initial displacement of the particle, or you know, stuff about the position of the particle, in other words. So how do you go from acceleration to velocity?
The acceleration is the derivative of velocity.
Yeah, so if I have S, V, and A, going this way involves derivatives, right? Going this way is going to involve
Antiderivatives.
antiderivatives. Okay. So V of t will be the antiderivative of A of t, right? So what's the antiderivative of 5 cosine t? Mm-hmm. And what's the antiderivative of negative 2 sine t? Plus 2 cosine t. And still plus, I don't know why I wrote cotangent, that's because I missed the s in cosine. 2 cosine t plus c. And now you know v of 0 is negative 6, right? So input that information. We get negative 6 equals 5 sine of 0 plus 2 cosine 0 plus c. And be careful of sine and cosine because plugging 0 into them does not yield 0 for both of them. Cosine of 0 in particular is 1. So that's negative 6 equals 0 plus 2 plus c, which implies, I think c is equal to negative 8. Okay, so my v of t function is 5 sine of t plus 2 cosine of t minus 8t, and that's, no, just 8, sorry, no t yet. So there's the velocity. So you go one more time because you got to go back to position. And position, the letter that they use for that is S. So and then you anti-differentiate the thing I have underlined in blue. So what's the antiderivative of 5 sine of t? Negative 5 cosine t, great. Plus 2 sine of t, right? Minus 8t, and you've already used c, so use a different letter, use d. And you know that s of 0 equals 2. So 2 will equal negative 5 cosine of 0 plus 2 sine of 0 minus 8 times 0 plus d. So 2 equals negative 5 plus d, which implies d equals 7. So your position function is negative 5 cosine t plus 2 sine t minus 8t plus 7.
That's the parent function.
That's the original function that was differentiated to get the acceleration function. And you could check it by taking the derivative, but that checking won't allow you to check the values of the constants. Unless you do so by like inputting this and seeing if it works and input that and see if it works. So, say that again? As a 7. Yep. Okay. So this question is kind of a baby step above the last question. It is quite similar. It's just you've got to pick out the initial velocity and the initial position from the equation itself. You've got to know a little bit about acceleration due to gravity. So a ball is thrown upward with a speed of 48 feet per second from the edge of a cliff that is 432 feet above the ground. Find its height above the ground t seconds later. So we're assuming that this person's on this cliff and the ball goes up and over the edge and then down into the canyon. So the thrown upward with a speed of 48 feet per second. That's an initial velocity. Does that make sense? That's like saying v of 0 equals 48. Does that make sense? What is the 432? Is the starting position. Does that make sense? The ball starts on that cliff, and we're assuming that the person's height is negligible, or maybe they're lying on the ground or something, who knows? But that tells you S of 0 is 432.
Does it help if, like, the acceleration is feet per second, like?
Yeah, we're gonna need some information for that, and I'll tell you that in just a moment.
Well, I mean, could you find what they're giving you by the units?
Yes, you can find what they're giving you by the units, yes. So like velocity will have units of measurement per unit of time. Yes, definitely. That's another hint. One thing that's not in this question but could happen on your homework, if something is dropped, the assumption there is that v of 0 equals 0. Like your initial velocity, if you drop it, is nothing. You don't put any velocity on it. If it's thrown downward with a velocity, that means the velocity is negative. Does that make sense? It has a sign to it. Okay, so now the thing that you need to start this problem is you need to know what acceleration due to gravity is in the non-metric units.
Are we
And-
doing 9.8 meters per second?
That would be if you were in metric units, okay? So if metric, A of t is negative 9.8, I know it's like 9.81, but it's negative 9.8 meters per second squared. Here, because we're in the feet world, it's negative 32 feet per second squared. So we're gonna use that acceleration due to gravity. And that's the function you begin with. So now given that, can you go backwards and find the velocity equation? What's v of t gonna be?
Negative 32t squared plus 48?
Just negative 32t plus, we'll say the first constant c. And then the 48 is gonna go in for the c. Does that make sense? So your v of t is minus 32t plus 48. Yes? Because we know v of 0 equals 48. So that's the same thing as 48 equals minus 32 times 0 plus c. And then 32 times 0 is just 0, so c is 48. Okay, so that's your velocity function. What is the position function? What's the antiderivative of minus 32t? Minus 32t squared over 2, or which is negative 16, right? Plus 48t plus d, or it's minus 16t squared plus 48t plus d. And you know that S of 0 is 432, right? So that's going to tell you that, what's the d? So your position is negative 16t squared plus 48t. Did you notice when we did problems that involved acceleration that they all had this negative 16 in them? Every single one? That's where it's coming from. That's coming from the acceleration due to gravity after doing this integration process. If it was the case that you were in meters per second, it'd be negative 4.9. That'd always be there. I just think the negative 16 makes problems that factor nicer, and that's why they do that. So, okay, so that is the position. The question has parts because they're mean like that. So it also wants to figure out when the ball reaches its maximum height and when does it hit the ground. So how would you figure out the max height? vertex, which would be the same thing as solving s prime of t, which is the velocity, equal to 0. So solve negative 32t plus 48 equals 0. 48 equals 32t. So t is 48 over 32, which I think you can divide those both by 16, you get 3 over 2. So after 1.5 seconds. And then it's falling, falling, falling for a long time. Okay, how about hits the ground? How would you figure that out?
0 is equal to the position function.
0 is equal to the position function. For 32. And I divided everything by negative 16, and I got 0 is t squared minus 3t minus 27, and I hoped that that factored, and it didn't. So I used the quadratic formula, and I got t is about equal to 6.9 seconds. So if I say qf next to that, does it make sense what I mean by that? Use the quadratic formula to solve it. It is easier to plug smaller numbers into that formula, though, isn't it? So I would say if you can, divide out constants that make your life easier to do that. I won't intentionally do that to you, but it might happen by accident. I don't do all your homework problems, and make notes, and write quizzes, and answer emails. Quadratic formula. Yeah. You. Okay, the next question is the question that is definitely a teensy bit hard, but I think it's kind of an interesting question to think about. So, a car is going 50 miles an hour, the brakes are fully applied, and that produces a constant deceleration of 22 feet per second squared. How far does that car travel before it comes to a stop? And that's all the information you need to solve this question. Which is kind of crazy, isn't it? Okay, it's really pretty awesome. Now, the first thing that makes us yep, they gave you the deceleration, which for some, maybe they could test in the lab or something like that. And they said, well, if this is the case, now one problem with this, the units don't match. And it got me for a bit there that I'm like, oh crap, I'm not getting the right answer. So we have to change units. And I'm gonna change 50 miles per 1 hour into feet per second. Yay, dimensional analysis.
No, I can change hours into seconds, but I can't.
It's
change-
seconds squared, and that's it's tricky to change square units. Don't try.
3,600.
Let's just not. Okay, so 50, I did the other way, so my work is that way. So how many miles are in? How many feet in 1 mile?
5,680.
Yeah, because what a random number, right? Okay, so we're now in feet. And then first you change your hours into, first I change them into minutes, because that's all the farther I can go. Hour, minutes, so 1 hour, 60 minutes, right? And then 1 minute, 60 seconds. So all this ends up being approximately 73.3. Probably repeating, but, and that's going to be feet per second. I mean, it's going to be ugly both ways. You're either changing your feet per second squared into miles per hour, or you're changing your miles per hour into feet per second. I think it's easier to change the one that's not a squared unit. Okay, so now you know that A of t is minus 22. Tell me if you agree with that. When you apply your brakes, it's a constant deceleration. Okay. And if you have the acceleration function, you can find the velocity function, right? So v of t is equal to minus 22t plus some constant c. And this 73.3, that's your initial velocity when you apply the brakes, right? So you know that v of 0 equals 73.3. So what's that c going to be? Great. So v of t is equal to minus 22t plus 73.3.
So just figure out where the velocity is 0? 'Cause that's when the car isn't moving, right?
That would be when the car is stopped, yes. Okay, so the car stops when v of t is equal to 0. Do you guys agree with that? Say that again?
Well, wouldn't it all be negative? Because, oh, no.
Okay, so set that equal to 0, minus 22t plus 73.3. You get 22t equals 73.3. T is about equal to 3.33 seconds. So it tells you how long the car takes to stop, 3.33 seconds. Is that the question that you were asked? You were asked how far the car went, right? This will be helpful, but it's not quite the answer. So if we want to talk about how far the car went, you've got to go back to the position equation. So S of t will be minus 11t squared plus 73.3t plus some d. And this is the step where we actually make a little bit of a jump that I think you wouldn't get unless I explain it. You assume S of 0 equals 0. Because you're talking about your position relative to where you start applying the brakes, right? So you can just say, well, the place where I start applying my brakes is, I've gone 0 feet, right? And so you can just say, okay, well, my initial position is 0 feet past where I started, which lets you give the equation as S of t equals minus 11t squared plus 73.3t. So that's the one thing that you might not have been able to like come up with on your own. And then can you now figure out how far the car goes 3.3 seconds later? Yeah, you just plug in 3.3, don't you? So you find S of 3.33, and that's about 124.3 feet. And it might just be because I'm really nerdy, but I think it's so cool that you can just, with only the initial velocity and the constant deceleration, figure out how far it takes you. Like, I think that's kind of a neat question.
And where's the d factor?
The d, there would technically be a constant here that tells your position equation, right? But you can think about that d as how far you have gone since you've applied the brakes. Does that make sense? I guess in some sense, because it's not actually quite that all the time, it's only that initially. You can think about that d as how far you have gone at time 0 when you apply the brakes. And you've gone nowhere. That's why you can assume S of 0 is 0, which gives you d equal to 0. That d, in these equations, that last constant with the, that's not always going to be true. For polynomials, it will. When you have something that's kind of like, it's a polynomial, for sure, this thing will always be your initial position. Yay, physics, exactly. But that doesn't work for things when your velocity and acceleration involve sine and cosine. Okay.